All right, what's up, everyone? Today we're going to continue in our discussion of combinatorics with 15.2. We're going to do three new counting principles: multiplication, addition, and complement. So let's jump right in because I want to make sure this video is a little shorter than the last one. So this is the first principle. It's called the multiplication principle. It's going to be very useful for us. If we have two different actions, all right, sometimes called events. So if we have these two different events that can each be performed in a certain number of ways, we're just calling those ways n sub 1 and n sub 2. Okay, the two actions can be performed together in n sub 1 times n sub 2 ways. You just multiply the two numbers together, hence why it's called the multiplication principle. All right, let's just jump into an example because it'll probably make a little bit more sense when I kind of go through an example. So if you have 4 hoodies and 2 pairs of sweatpants, the classic quarantined at home outfit, how many different quarantine outfits can you make? Okay, so we have kind of our 4 different types of hoodies, okay, which I will just name the letters A, B, C, and D. All right, so there's 4 different possibilities for the types of hoodies you can wear. All right, and this is you. I'll kind of start making, it's called a little tree diagram here. All your options. And for each hoodie that you wear, there's 2 different sweatpants you can choose from. So I'll name those 1 and 2. All right, so notice if we count up all of those options down here at the end, we just get 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 possible outfits. Okay, you could have also got that by just using that multiplication principle. There's the first event can be performed in 4 ways, wearing one of your 4 hoodies. The second event can be performed in 2 different ways, and 4 times 2 is 8. So there's 8 possible outfits. Easy enough. Okay. So this one's going to be slightly different. So we have, in how many ways can 8 people line up in a cafeteria? Okay, so it's going to be still using that multiplication principle. So let's kind of think about, so we'll have kind of 8 slots. 1, 2, 3, 4, 5, 6, 7, 8. All right. So let's think about this. If there's 8 total people, and there's how many different ways can those 8 people line up in that first slot? Well, it's going to be 8 because there's 8 options. For this second slot now, since one of the 8 people already lined up in our first slot, we only have 7 people remaining. Okay, going forward to the third slot, well, now 2 people have been taken up. Okay, so now there's only 6 people remaining. Sure, you can kind of start getting the pattern here. 5, 4, 3, 2, 1, until we get to that last kind of person. All right, so each of these events, lining up for that first spot, lining up for the second spot, lining up for the third spot, we just need to multiply down the row. So it's just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which you would get 40,320 ways. Which seems like quite a bit for just the number of ways that 8 people can line up. All right, so don't be alarmed when you start getting some seriously big numbers here, okay? A lot of times the results from these combinations type problems are very large, so don't let that be surprising to you, okay? So what we just did there is something called a factorial, okay? Represented by this exclamation point. It's not the English usage of the exclamation point where we're yelling. We're not going n. All right. This is called what's called n factorial. So what we did on that last problem was what we did is called 8 factorial. All right. We're not yelling 8. It's called 8 factorial. And that was just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? In general, n factorial is just the value n, and you're subtracting 1 all the way down, all right, from the previous value, multiplying down that row until you get all the way to 1. Okay? Here's a special case. 0 factorial is defined by definition as equaling 1. Okay, so that may be kind of counterintuitive to you, but that is what 0 factorial is by definition. Okay, every other factorial you just calculate. So like 3 factorial, to do an easy one, would just be 3 times 2 times 1, which equals 6. Okay, as you can see, factorials get very large very quickly. All right, and they have a lot of important usages in these combination problems. Okay, we saw in the last problem that 8 factorial was 40,320. Okay, so they get very big very quickly. Let's do another example here. So I don't know how many you live in DC. I do. Here's how our license plates are set up. We have 2 letters that come first, and then 4 numbers. I want to know how many total possible DC license plates are there. All right, are we close to running out? No, they're still on. I believe they're still on F, so we got plenty left. But let's kind of figure it out. So we have, once again, I'm going to set it up very similarly to how I did the cafeteria problem. So I have the first 2 slots are letters, and those last 4 spots are digits, so the 4 numbers. And so repeats are allowed here. Okay, so just because I choose F for my first letter doesn't mean I can't have F here. Okay, so for these letter spots, it's going to be 26 and 26. And then for the numbers, same thing. All right, repetitions allowed on these license plates. Just because we have a 9 here doesn't mean we can't have a 9 here. And so there's going to be 10 digits, okay? So you got to think 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 total digits for each of those slots. Repetitions allowed. And then we're just going to use that multiplication principle again. So just 26 times 26 times 10 times 10 times 10 times 10. All right, and what I got from multiplying all that together, 6,760,000 license plates. Okay, since there's not even close to that many cars in DC, I think we are safe for a long time until we run out. All right. So let's move on to the second principle here. It's called the addition principle. We're going to need a little bit of vocab first. This word mutually exclusive. So if 2 events are mutually exclusive, it means they cannot occur at the same time. Okay. So things that would be mutually exclusive, it would be like flipping a heads and flipping a tail. Okay. If you're flipping a coin, you cannot flip both at the same time. So those 2 events are mutually exclusive. And so if these 2 actions are mutually exclusive, and the first can be done in n1 ways and the second in n2 ways, then one action or the other can be done in n1 plus n2 ways. So addition principle, we got some addition going on. Okay, and it's probably going to make sense when I just kind of make more sense when I can kind of show you an example here. But the important thing is that mutually exclusive is key here. All right, so we can't have any overlap. Another fun word for mutually exclusive that means the same thing is disjoint. So if you see the word disjoint or mutually exclusive, those mean the same exact thing. It means that these two events, two actions, cannot occur at the same time. Another example is for like the hoodie and sweatpants. You can't wear two of the hoodies at the same time. So the different hoodies are mutually exclusive. The hoodies and the sweatpants would not be. And the last counting principle is called the complement principle. Okay, we know the complement is when something's not happening. Okay, the book uses this A bar notation. Okay, a lot of times you might see this as well, A with a little C. Those mean the same thing. Those both mean A complement or not A. And so this complement principle says if A is a subset of the universal set U, then the number of outcomes in A is equal to the total universal set minus the number of outcomes that are not A. Okay? So when you kind of read it that way, this kind of seems like common sense, and it is. But this is going to be very valuable to us in probability and these combinatorics problems, because it can really kind of simplify the problems for us if this is very easy to figure out. Okay, a lot of times a good cue to use this is when you see the words at least in the problem. Okay, so if you see those words at least, it's probably going to be a good cue to use this complement principle, because it's going to probably be pretty easy to figure out the number that are in not A, and then you can kind of work backwards to figure out the number that are in A. Okay, remember these n's are just all that means is the number. So this is just the number in set A equals the number in the universal set, that's just our total, minus the number that are in A complement. All right, so this is an example of using that complement principle. So we have find the number of 4-digit numbers containing at least 1 5. All right, so let's kind of work backwards here. Since I have that word at least, okay, I'm going to want to use that complement principle. Okay, so let's kind of set it up. The complement principle, remember, is just the number in A. Okay, so if the universal set, we're going to call the universal set all possible 4-digit numbers. So to figure out the number of all possible 4-digit numbers, let's kind of do that work right here. So if it's a 4-digit number, there's going to be 4 slots here. Okay, and so a 4-digit number, it can be, that first digit can be any of those digits except for 0. If that first digit is 0, it's not a 4-digit number, it would be a 3-digit number. So there's going to be 9 possibilities for that first slot. And then for every other slot, there's going to be 10 possibilities. So it'd just be 9 times 10 cubed, which would just be 9,000. All right, minus the number not A. Okay, so we basically need to figure out the number of 4-digit numbers that contain 0 5s. Okay, because if we subtract out the ones that contain 0 5s, that'll leave us with the number that have at least 1-digit 5, meaning they could have 1 5, 2 5s, 3 5s, or 4 5s. So the number containing the number that hold on. So the number of containing 0 5s, it's still 4-digit numbers. So the first slot now it was originally 9, okay, because it couldn't be 0. Well, now it can also not be 5, so we're going to need 8 there. All the other digits, every number is totally fine except for 5. So instead of having 10 for each of those slots, we'll now have 9. So that's just 8 times 9 cubed. which gets us 5,832. So to figure out the number that contain at least 5, we just do 9,000 minus 5,832, which would get us 3,168. Okay, using that complement principle made that work a lot easier on us. Okay, we didn't have to kind of, if we had to do it the other way, we would have had to do, okay, let's find all the possible 4-digit numbers with 1 5, plus all of them with 2 5s, plus all of them with 3 5s, plus all of them with 4 5s. Okay, so using this complement principle is going to be quite valuable, make the work easier for us. Remember, whenever we see that at least in the problem, that's going to be a good sign that it's going to be a good idea to use that. All right, last example. We got 3 parts. Given the digits 0, 1, 2, 3, 4, and 5, how many 4-digit numbers can be formed if A? All right, so let's just work with A. If the digits can be repeated. This one's going to be pretty straightforward. So we have 4 digits. And if this is a 4-digit number, okay, so once again, the first digit cannot be 0 here, okay? But there are 1, 2, 3, 4, 5 other options. So that first is going to be 5. And then for the other ones, 0 is totally allowed, as are every other number, because digits can be repeated. So it's just 5 times 6 times 6 times 6. So 5 times 6 cubed, we would get 1,080. That's the answer to part A. Pretty straightforward. Very similar to the other ones we've done. The second one, digits cannot be repeated. All right, so once again, we're going to have 4 slots. We still want a 4-digit number here. All right, and so the first number is going to be the same. It can be any of those 5 other digits. It still cannot be 0. The second digit is going to require a little more thought here. So we chose one of 1, 2, 3, 4, 5 for that first slot. Okay, so now we have 4 of those left. But we can add back 0, because now 0 is allowed for the second slot. So we're going to have 5 for the second slot. And now we've chosen 2 of our 6 total numbers. So 6 minus 2 is 4. And to the fourth slot, we've now chosen 3 of our numbers from slots 1, 2, 3. So we only have 3 left. So 5 times 5 times 4 times 3 will be 300. Okay, just something to notice right now, maybe obvious, but when things can be repeated here, you're going to get a lot more combinations when things cannot be repeated. Okay, so just something, just a pattern to kind of look out for these ones. All right, so C is going to require a little bit more work. So digits cannot be repeated, and the number must be even. Okay, so for the number to be even, and out of our possibilities, it must end in 0, 2, or 4. Okay, so what I'm going to do is kind of treat each of those separately. Okay, because those are what we call mutually exclusive outcomes. All right, and then I can just add them all up at the end to get the total number. Okay, so let's get the first ending in 0 one here. So we'll have 4 digits. All right. So if it's ending in 0, that last number is locked in as 1. Our first digit, okay, so it can be any of the numbers 1, 2, 3, 4, or 5. It cannot be 0. So there'll be 5 options for the first one. Okay, and so the second digit, we got to kind of think. It cannot be what we chose for our first number, and it cannot be 0. So it's going to have to be 4 total possibilities. For our third number here, it cannot be the number we chose first, or the number we chose second, or 0. So there's only 3 options. All right, so 5 times 4 times 3 times 1, that's going to be 60. Okay, let's do the same thing for, so we handled the ending in 0. Let's do ending in 2 now. We'll set up our 4 slots again. Once again, the last digit must be 2, so that's locked in as 1. So now for our first digit, it cannot be 0 once again, but now it can also not be 2. Okay, so we only have 4 options for that because the digits cannot be repeated here. Okay, so for our second one, 0 is totally fine now. 2 is still not. And whatever we chose for this first digit is not okay. So that leaves us with 4 additional options. The third one, I'm sure you're picking up on the pattern now. It cannot be 2, which we have locked in here. It cannot be either of these 2 that we've used up here. So that's just going to be 3. So 4 times 4 times 3, that'll be 48. All right, so we did 2. Let's do 4, last one. Set up our 4 slots again. We know the last number is going to be 4, so that's locked in as 1. And this is going to pretty much carry that same pattern as the 2 one, okay? Because we know the first digit cannot be 4 or 0, so that's going to leave us with 4 options. The second number, 0 is back introduced, but we already used one of the digits here, so we're down whatever we had our first number be, and we're down 4, so there's going to be 4 possibilities left. And for our third number, we can't use either of our first 2 digits, and we can't use 4, so that's going to be 3 possibilities for another 48. So to tap it all off, to figure out the total number, we just got to use addition principle, add up each of those mutually exclusive outcomes, 60 plus 48 plus 48, and we would get 156. And there we go. That's all I got. Thank you.